Hi, let us see some interesting differentiations. Here we will see a new techniques or rather some interesting techniques for finding derivatives. Our aim is to find derivatives because many of these results are clumsy and it is very difficult to remember, and more we are trying to remember, the more is the chance of mistakes. So let us remember less and let us formulate techniques to approach the problem, which will be very easy in attacking the problem. Okay, now let us start with that. First thing what we are going to see is some basic rules of differentiation. Basic rules for differentiation. One thing first, in this subheading A, it is product rule, right? What do you mean by product rule? That is, if I have to differentiate f of x into g of x, I will get f dash of x into g of x plus g dash of x into f of x. That is, when I differentiate a product, I keep one function as constant and differentiate the other. Then I differentiate the other function and keep the other one as constant. Correct? This is, then there is something called quotient rule. What this quotient rule means? That is, differential of u by v is nothing but, if I have a u by v form, I will get denominators, whatever is the function in the denominator, that square into vu dash minus uv dash. These are very important basic rules. We should remember this. Then the third thing is called chain rule. Here, differentiation of f of g of x is nothing but f dash of g of x into g dash of x. That is, if I have a function of a function, then I differentiate the outer function, then I have to differentiate the inner function, then I proceed like this. See, for example, if I differentiate, let me differentiate cos x. What is differentiation of cos x? Differentiation of cos x is minus sin x. No, we don't stop here, right? Do we? No. No. Then what is differentiation of cos x? This is wrong. The correct answer is differentiation of cos x will be, first I differentiate the function cos of x, that is minus sin x. Then, no, it is not complete. We have to differentiate x. X is another function. It's an algebraic function. So differentiation of x will be dx. Correct? So therefore differentiation of cos x is not minus sin x. It is minus sin x dx. This is the correct answer. This is correct. So with this introduction, let us see some interesting differentiations. Okay. So let me give an introduction example. Let me give an introductory example. So y is equal to sine inverse of x. Find dy. Now we are not aware of how to differentiate sine inverse of x. See, remember always one thing, whenever we find situations like this, convert this problem. This is not only the whatever technique I am telling is not only true for this problem, it is true for any problem. Convert the problem to a known form and solve it. Now sine inverse of x is an unknown form to me. What is known to me? Sine x is known to me. So let us convert a problem of sine inverse to a sine. So how can I write this? I can remodel and write this as x is equal to sine y. Correct? Now differentiate both sides. On differentiation, what we get? Dx is equal to cos y dy. Now I need to find dy. Correct? What is dy? Dy is what? 1 by cos y dx is equal to dy. Now what does this mean? What is cos y means? For that we go back to our basics. We know that sin square theta plus cos square theta equal to 1. So therefore cos theta will be root of 1 minus sin square theta. Correct? So apply that here. So dy will become 1 by sin y is x. Sin y is x, right, here. So what will be cos y? Root of 1 minus x square. So this is the answer. Now let us not stop there and continue seeing this technique for some more problems. Let us take y is equal to cos inverse of y, cos inverse of x. Let me write it. Y is equal to cos inverse of x. Find dy. Now how do we solve this? Again we convert it into a known problem. So what do I know? I know the derivative of cos x. So if I rewrite it, x is equal to cos y differentiation will give what? This step. Dx is equal to minus sin y dy, and dy is equal to minus 1 by sin y into dx. That is nothing but again going from the basics, sin square theta plus cos square theta equal to 1. Therefore sin theta will be root of 1 minus cos square theta. So cos y is x. So sin y will be minus 1 by root of 1 minus x square dx. See, this technique, it hardly take, when in full practice condition, this derivative will take 15 seconds to solve. Rather than remembering this and reproducing it in the wrong form in the exam, if this comes, we can spend 15 seconds and definitely solve this problem to avoid mistakes. Because these type of structures are very clumsy to remember. I will show how clumsy it is to remember this thing, because the more we try to remember, the more is the chance of making mistakes. So let us solve one more thing. Y is equal to sec inverse of x. Find dy. How do we solve? Again convert it into a known problem. X is equal to secant y, which will imply dx is equal to what? Differentiation of secant y will be secant y tan y dy. Again we are doing function of function. First I differentiated sec y, then I am differentiating y, because it is not sec y, it is secant is a separate function and y is an algebraic function, which is another separate function, correct? So we get this. So from this we get dy is equal to 1 by secant y tan y times dx. Again let us go back to the basics. The basics is sec square theta minus tan square theta equal to 1. So I already know what is secant y. I need to find tan. So tan theta, tan square theta will be sec square theta, sec square theta minus 1 will be tan square theta. And tan theta will be root over sec square theta minus 1. So using this here, dy will become 1 by secant y will be, secant y is x, and tan y will be x square minus 1 what dx. This is the answer. See how the structure is. One problem we get x square minus 1, in other problem I will get 1 minus x square. Moreover there is a minus sign here, there is no minus sign here. So when we try to remember all these things and reproduce in exam, the chance of making mistake is more. So we will understand these type of quick techniques to find and solve the problem and approach it in a much easier way. Okay, fine. Now let us take one more problem. Y is equal to log to the base x a. This is another interesting thing to solve. If I have log x to the base a, that is different. Here I have log a to the base x. What do I mean by log a to the base x? First I need to simplify this to a known form again, correct? So again we always go back to the basics. What does the basics say? If I have log b to the base c, this is nothing but log b to the base e by log c to the base e, correct? Going in the same sense, I can convert y as log a to the base e by log x to the base e. Now log a is a constant. This is the variable term, correct? So this is nothing but y is some log a base e into 1 by log x to the base e. This can be solved very fast. How do I solve it? It is something like a u by v form, where the u is a constant, correct? So I can solve it as y dy is equal to, how do we solve for a u by v form? We use the quotient rule, correct? Log a to the base e is constant. We keep it outside and we get the denominator square, right? Log x to the base e the whole square into vu dash, right? What is the formula we are using? Differentiation of u by v is equal to v square vu dash minus uv dash, correct? This is the technique we are using, correct? This is the technique we are using here. So the v square part we have written, then the v here will be vu dash we have to write, right? So log x to the base e into differentiation of 1. Differentiation of 1 is a constant, this will become 0 minus 1 into differentiation of log x to the base e, that will be 1 by x. This is the numerator part. So finally on simplification we will get this whole part will become 0. So we will get minus 1 by x into 1 by log x the whole square. This is very important. And this whole term is having a constant outside, that is log a to the base e. So this is the dy. This is the answer. This can be further simplified. The algebraic simplification can be done, but we stop here for the sake of answer.